Welcome to the next webinar in my series on modern Java by example. Today, we're going to pick up where we left off yesterday, and we're going to focus on the completable future variants of the ImageStream application. So let me go ahead and share my screen, and we'll start by taking a quick look at the code where all this stuff resides, which is right here. So if you go to my GitHub repository, which is shown at the top of the slide, and then you go ahead and go down here a little bit, you'll find the ImageStream application. And if you go inside ImageStream and the command line version of this program, and then you go a little further down there in the main portion, you'll see that in this we've got a number of different implementations for doing the ImageStream downloading and processing and storing. And the particular examples we're going to look at the beginning of today are going to be Completable Future 1 and then Completable Future 2. So that's what we're going to talk about this afternoon. Okay, so let me then pop over to my IDE. And you can see here that we have what we left off with yesterday. This is the main driver program where we have all the different tests we're going to run. So let's go ahead and take a look at Completable Future 1. There are two different variants here. One uses completable futures in conjunction with sequential streams using mechanisms like collect and so on. And then the other variant is going to use completable futures with streams, but within a variant of this. And it's going to use some other mechanisms we'll talk about. The two approaches are quite different. They both perform very well. When you run the test program, which we did yesterday, you can see that they both give very good performance and outperform the parallel streams version. You'll also notice as we walk through the code here that this is more complicated than the parallel streams version, which is perhaps no surprise because completable futures are a harder mechanism to program. But hopefully the pain is worth the gain, as we'll see here. Okay, so here's ImageStream or ImageStream Completable Future 1. It inherits from a helper class, a superclass called ImageStream Completable Future Base, and this contains some methods that are used by both implementations we're going to look at. There's something here that checks to see if a URL is cached, and we have a way to log results. Those are basically the things we're going to share here. Let's go back over here, and we'll take a look at the constructor. The constructor is very simple. It just goes ahead and calls up to the superclass constructor, passing in the array of filters and the iterator that contains the images we want to process. Let's go down here to initiate stream. You can see here what we're going to do is we're going to set the executor to be the common fork join pool. This becomes important because with the other version we're going to look at, we set the executor to be just a good old fixed size thread pool. So in this case, we're using the common pool, and that of course means we can expand and contract this by using the managed blocker mechanisms we've talked about before. Then we go ahead and initiate the stream, and that will ultimately end up causing the process stream method to get called back. This is the hook method. And what this hook method does is it gets the list of URLs that were provided by the user, and then we convert those URLs into a stream of URLs. So we have a list of URLs, we turn them into a stream of URLs. And that's where the fun begins. So up to this point, it looks pretty much like what we had before when we had shown the parallel streams version. Two things are different. Number one, we're using sequential streams here. And number two, we're getting parallelism by using the completable futures framework and the various mechanisms it provides. So we'll start off by taking a look at something called check URL cached async. And this particular method, as we'll see in a second, is going to asynchronously check to see if a URL is already cached. So remember, the whole point of this is to ignore images that have already been cached. So we're going to ignore cached images. So let's go ahead and take a look at checked URL cached async, which is just down a little bit down here below. So let's go ahead and take a look at this. So here is check URL cached async. You can see it takes a URL, and it's going to then go ahead and use the completable futures supply async factory method to run this call in the background. And this call is something called URL cached. We'll look at that in just a second. that code is actually identical to what we saw with the parallel and sequential streams version we looked at yesterday. So what we're going to do is we're going to go ahead and do this call. This call will take place in the background in a worker thread in the common fork join pool. And we know that because getExecutor is going to return the common fork join pool that we used to initialize this earlier. So this particular action is going to run in a thread in the background in the fork join pool. And we'll take a look at what it does in just a second. But what it's going to do is it's going to take the results of URL cached and it's going to wrap it up inside of an optional. And we'll talk in a moment about why we use optional here. It has to do with some interesting quirks about the connections between streams and completable futures. But first, let's go ahead and take a look at the URL cached method. Let's go look at its implementation. So here's URL cached. This is just what we had the other day. I suppose I could have rewritten this to use completable futures too, but I already had the code that worked just fine. So what it does is it takes the list of filters and then goes ahead and uses a stream factory method to turn this into a stream of filters. And then we go and we check to see whether or not we already have files with these names in our file system. And if you take a look here, this is the same code we looked at the other day. It just checks to see if there's already a file with that name. If there's already a file with that name, it's been cached. If there's not a file with that name, it's not been cached, in which case we want to keep processing it. Okay, so let's go ahead and kind of pop back up here. So check URL cache, as we just saw. What that's going to do is that's going to go ahead and call this URL cached method. That's going to either return null if the item has been cached. Sorry, it's going to return true if the item is cached and false otherwise. So if it is already cached, we're going to make the optional be null. In other words, no value present. If it's not been cached, we're going to make the optional hold a URL. And there's a factory method on optional called ofNullable, which either takes a value or a null and then creates the appropriate type of nullable from the ofNullable factory method. And the whole point of this is we want to either have an empty optional if we've already seen this element and it's cached, and we want to have an optional that has the value present if we haven't seen it before. So this whole thing is going to kind of run in the background. It may take a few milliseconds or so on to do this check. So we run this via supply async. So this is running in a background thread. And so what we get back from this, of course, will be a completable future to an optional URL. So that is what checked URL cached async is going to provide us. So what we're going to get back out of this, as you can see from the code in my IDE, the signature of the stream, we have a stream of completable future of optional URLs. That's what gets passed out of map. And then we turn around and we take that stream of completable futures to optional URLs and we feed it through the map intermediate operation, passing in the download image async method. And we'll look at download image async in a second. And you'll also see in a second why we're passing around a stream of completable futures to optionals. And it's actually very clever. So let's go ahead and take a look. So let's pop down here and go to the implementation of download image async. And you can see that download image async takes a completable future to an optional URL. And when that future completes, in other words, once we've figured out whether or not this item is in fact cached or not, then we're going to go ahead and have this completion stage method invoked. And this completion stage method is past this action. And what this action is going to do is it's going to take the optional URL, and if in fact it's not empty, in other words, if there's a value present, in other words, if it wasn't cached, then we're going to go ahead and perform a blocking download. So if it's an empty optional, then map turns into a no op, and it just returns an empty result, an empty optional as a result. But if it's not empty, then we go ahead and download the image. So we're downloading non-cached images. And if you remember blocking download is something we also looked at the other day. It basically uses the call and manage block method to download the image, and it'll expand the threads in the fork join pool, the common fork join pool, in order to do that. Okay, so that's basically what this operation does. And this particular operation is being called with the then apply async method, which runs this action asynchronously in a worker thread in the common fork join pool. So this downloads, all the download operations will also be taking place essentially in the background in a worker thread. So all those optional URLs that have values in them, in other words, they weren't cached, will all be asynchronously downloaded. And the return value from this method is a completable future to an optional image, because once we've downloaded the contents at the URL, we convert it into an image. Okay, so that comes back here. So now what we have, as you can see, is we have a stream of completable futures to optional images. So before we had a stream of completable futures to optional URLs. Now, after doing the download image async method, we have a stream of completable futures to optional images. And now we're going to go ahead and do yet another asynchronous set of processing. We're going to call the apply filters async method. And this is going to take the stream of completable futures to optional images, and it'll go ahead and return a stream of filtered images that have not already been cached locally. So we're going to see in a second how all of this stuff works, and it's really cool. You'll also notice a little parallel structure here. If you go back and look at the parallel streams and sequential streams implementation from the other day, you'll see that there also was a call to something like check URL cached, except it wasn't async. There was also a method that did download images, but it wasn't async. And there was also a method that applied filters, but it wasn't async. So now that we're using completable futures, everything's going to run asynchronously. Okay, so let's go ahead and take a look here. Let's go to the implementation of apply filters async. This is a particularly interesting method because it takes a completable future to an optional image, which we call image future. And then what we're going to do is inside the body of this method, we're going to go through each of the filter objects to do grayscale, no-op filter, the null filter, emboss, sharpen, ivory, whatever your favorite image filters are. And for each of those filters, we're going to take the filter, and then when the image has finished downloading, we're going to go ahead and asynchronously apply the image that we just got, that just finished downloading, to the filter. And we're going to do this running in the background, again, in the common fork join pool. And we're going to go ahead and use the map operation on the image optionals. So the image optional, again, if it's empty, if it was cached, it's a no-op. If it's not empty, if it's non-cached, and we downloaded it, we go and we had apply this thing called the filter decorator with image. And it's basically a transform that converts the downloaded image into a filtered image and has the side effect of storing it in the file system. So that all takes place asynchronously, running in the background, once again in the common fork join pool, because that's what getExecutor returned. So then apply async, we'll have that scheduled and run in the background. And here, you'll notice we have no terminal operation. So this actually returns a stream of completable futures to optional images. So that's pretty exciting. So what are we going to do with that? We're going to take that, and we're going to go ahead and flat map it. So we're going to take we're basically going to come out of this with a stream of images that are in the midst, or a stream of completable futures to images that are in the midst of being essentially filtered, transformed, and stored. So that's what we have here. So we get basically a stream of completable futures to optional images. So then what we're going to do is we're going to use this toFuture operation. And the toFuture operation is defined over here in utils. And it's basically the stream of futures collector. And we've looked at this before, so I won't dwell on it a whole lot here. If you go back and watch the previous videos, I've used this particular class over and over again when combining completable futures with streams. And the money shot here, the really interesting method is the finisher. And you can see here, here's the finisher method, as we can see. And what that does is it basically uses the all of arbitrary arity method that's part of the streams, the completable futures framework, in order to go ahead and create a completable future that will wait for all the other completable futures to finish. So all the things that are in the process of being checked for cached, in the process of being downloaded, in the process of being filtered and stored, all those things, all the different images running asynchronously in the background are all going to be now waitable from a single completable future. And that's the one that comes back from all of. And when all of returns, we're then going to go ahead and apply this completion stage method, which will take the futures, the completable futures we've got, and join them all together. And we're going to end up returning a stream, we're going to return, sorry, a completable future to a stream of images. That's what's going to come back from this particular method. So what that does is it basically, we did kind of a scatter gather operation. We scatter everything off. They're all running asynchronously. And now we're going to gather all the results back together again using collect. So we'll end up ultimately with a single method here, sorry, a single future, a single completable future. And when that one completes, that means everything is done. So we're done with the entire processing of everything asynchronously, in which case the then accept completion stage method gets called with the result of this stream. And then we take this stream and we use the Java 9 feature with Flatmap and optional stream. So if you combine Flatmap and optional : stream in Java 9, that will have the side effect of removing anything that's empty. So anything that was an empty optional will get removed from the stream. It's kind of like a filter. And then we take the size of this result and we go ahead and log it. Now, if you don't have the luxury of using Java 9 or beyond, if you're using Java 8, you'd have to replace this Flatmap optional : stream call with a pair of calls where you first filter to only let present optionals through, and then you'd have to use map and optional get. So it's a little bit more crufty in Java 8, but in Java 9, they cleaned it up. Also, if you're programming in Android, you have to use the Java 8 features because they haven't gotten with the Java 9 program yet. The final thing that comes back after all of this stuff is a single completable future, and we just go ahead and join on it, and that'll wait for everything else to be downloaded, processed, and stored. So that's the one and only place that we block. Everything else runs asynchronously, and all this cool magic happens. So that was the walkthrough of the ImageStream completable future 1.java variant of this, that particular strategy. So what I'll do now is I'll see if there's any questions, and then I'll jump in and talk about the ImageStream completable future 2 implementation, which is also very cool. Let's see if we have any questions. Why do we have to call it getExecutor after map? So the only reason for using getExecutor here was just I was making it possible to parameterize the executor. So let's go ahead and sneak back over here, and I'll reshare my screen and show you what I mean. I probably didn't explain this very well. I think you're probably referring to this call. So what this is calling then apply async, and we're past the optional URL once the previous stage completes. Now we have an optional URL. And then the 2 parameters that you need to pass to then apply async are the thing you want to run in the background, which in this case is to apply the map call on the URL optional. And you also pass another parameter, which is the thread pool to use. Now, I could have omitted this thread pool altogether. I could have just said this. That would have run it in the common fork join pool. That's the default behavior of then apply async and then compose async and supply basically, so you know, the other factory methods that are going to do the processing, like supply async and so on. In this particular case, I wanted to make it possible to override what executor I was using. So I just have a method called getExecutor to pass in there, but that's not necessary. It's just what I chose to do so I could parameterize this. And you'll see how in the next example, the ImageStream completable future 2 version we're about to look at, I do in fact have a different executor. I have a fixed thread pool instead of the common fork join pool. So that's just because I happen to want to make that parameterizable. So the next question is, Map, filter, map, layered logic introduces complexity into code. Are there any patterns available to reduce it? Yes, use parallel streams. If you want to avoid all the complexity of the completable futures framework with all these sort of nested calls, then you're well advised to stick with parallel streams. And the reason why parallel streams is the way to go is that everything there is synchronous, and so it's much easier to reason about your code. It doesn't get all this nested complexity. The minute you start using completable futures, you get the ability to write things that are going to be more efficient and more scalable, but the dark side to this is that it's going to be more complicated, and it requires you to sort of think in an inverted sense. The great thing about completable futures, however, is you can treat asynchrony in a reasonably synchronous looking way. So what the heck do I mean by that? So if you take a look back over here at the code, especially the code that we see that's like this, where we're doing download image async, apply filters async. Those calls, while they're running asynchronously, are joined together using the streams framework and the completion stage methods of completable future to look pretty synchronous, even though it's taking place behind the scenes. You'll see when we talk about the RX Java version tomorrow that this ability to turn asynchrony into synchronous looking code is really the virtue of the reactive programming models that you see in more and more today. It's still not quite as clean as purely synchronous code, but it's getting so close that if you know the tricks, it's not too hard. Okay, so that's basically ImageStream Completable Future 1. Let's now pop over and look at ImageStream Completable Future 2. And this is a really different one. This is quite a different implementation. The intent here was to try to avoid using collect. I was trying to see if I could avoid using collect wherever possible, just for kicks. So and I also wanted to get rid of all these optionals. I found the optionals were a little confusing in the other implementation. So first, let's take a look at the initiate stream method. This is a hook method that's called when the framework starts the ball rolling. Here, we're going to go ahead and make ourselves a thread pool, which is going to be the min of the number of filters times the input size, or S max threads. So whichever one of these things is smaller, that's what we're going to go with. We then go ahead and we make ourselves a new fixed thread pool. So a fixed thread pool is just a thread pool that pre-spawns a fixed number of threads. So with that in mind, now when we are going to call the various methods, the factory methods that make asynchronous computations, we're going to pass in getExecutor, except this time getExecutor is going to return this fixed size thread pool instead of the common fork join pool. So let's take a look at the code. First of all, you're going to see it's very different looking from before. So we get the input, and then we take the URLs that come from the input, we turn them into a stream of URLs, and then we're going to go ahead and make the map call passing in check URL cached async. That call is essentially what we had before. So we're going to get back a stream of completable futures to optional URLs. And what will happen there, of course, is in that stream, some of the URLs are going to be essentially empty if we've been cached earlier, and other URLs, other optionals are going to be non-empty if we had not cached before. So then what we're going to do is we're going to take that stream of completable futures, and we're going to call this really interesting helper method called join all stream. And that's defined here in this basically streams utils class. And if you take a look, there's a method in here called join all streams, or join all stream. And what it's going to do is what I show here. It takes a stream of completable futures to items of type T and returns a completable future to a stream of items of type T. So it kind of inverts things. And the way it does that, this is really super cool. So we go ahead and take the stream method, or the stream parameter, and use the toArray factory method on it. And we go ahead and get ourselves back an array of completable futures of type T. So we convert the stream into an array of completable futures. Then we take that array of completable futures and we go ahead and call the allof method. Allof is that fancy arbitrary arity method that returns a single completable future that triggers when everything that was passed in the array of completable futures all complete, when they're all done. So in this particular case, we're waiting to check to see whether or not the images were cached. We then take the all done future, and when it gets triggered, it's then apply completion stage method is called, and we convert the futures array using array.streams into a stream of completable futures, and then we go ahead and map them using completable future join. And that'll then, of course, return the actual objects to which they point, which in this case would be the optionals that we were talking about before. Okay, so that's what we're going to get back here. So if we go up here, we're going to see that this thing is going to come back essentially with a completable future to a stream. And when all the things that were being checked to see if they were cached or not are done doing that check, we're now going to have a stream of essentially completable futures. And what we're going to do is we're going to then remove all the optional URLs. So actually, I take it back. We have a stream of optionals, not a stream of completable futures, a stream of optionals. So we have a stream of optional images. And then we're going to go through and get rid of everything in here that was empty. So we're just going to have essentially a bunch of non-empty optionals. And then what we're going to do is we're going to go ahead and call download image async. And this is going to be a slightly different version of download image async because we managed to get rid of everything that was empty from before. So we'll take a look and see what that's going to look like here. So let's go ahead and poke down here. And you can see that we end up with download image async, which takes URLs, no longer optional URLs, because we got rid of all the ones that were empty. So now we have real, true URLs that were not cached. And then down here, we're going to go ahead and do supply async, passing in the download image lambda expression. And this is not the one that uses the blocking task. This is just good old download image. It just downloads it. And the reason we're not using blocking task here is because we're using the executor that's associated with the fixed size thread pool rather than the common fork join pool. We don't want to use the blocking task mechanism unless we have the common fork join pool, which we don't have here. So this will go ahead and download it, that each image in the fixed size thread pool and return a completable future to that image. So when that comes back, we're then going to have a stream of completable futures to images because we transformed them. And that will then get mapped with apply filters async, which is also a variant of the apply filters async method we looked at before. And again, what's different here, as you can see, is that the apply filters async method this time takes a completable future to an image rather than an optional image, because we don't have to worry about that. We got rid of all the optional stuff that was empty earlier. And then down here, we're going to go ahead and use the ThenCompose method. And this is just to illustrate another technique. We could also have used then apply async, but instead we're going to use ThenCompose in conjunction with supply async. So check out what we're doing. This is really funky. And in fact, it's actually probably worthwhile to look at the implementation of this method in the other class. So the other class we had, this is the first one we looked at. Notice what we did is in that implementation of apply filters async, we iterated through each of the filters, and then when the image future was ready, we did then apply async. So that's what we did previously. What we're going to do this time is when the image future is ready, we're then going to go ahead and iterate through all the filters inside ThenCompose, and we're going to go ahead and call supply async on each of the filter image pairs. So supply async will then go ahead and run the make filter decorator with image objects run method in the thread pool, the fixed size thread pool as designated by getExecutor. And that will then go ahead and run in the background, and that's going to end up returning a completable future to a stream of images. So this is just a different way of doing what we had done in the previous implementation. And as you can see, they both perform very well. So it's just a matter of taste and which approach you like better. So I was trying to do as many different things here as I possibly could. So then what we get up here is we're going to have the result of this set of operations will be a stream of completable futures to streams of images. So that's pretty wacky. So what can we do to make it unwacky? Well, what we're going to do now is we're going to use join as stream again. Remember, we used it up here earlier. So we had used join as stream, or join all stream, sorry, join all stream. We used it earlier. And now we're going to use this method again. And at this point, we're going to go ahead and pull everything together. So then we're going to end up essentially with a stream of streams, or a completable future to a stream of streams. So we're going to have a completable future to a stream of streams of images that are in the process of being downloaded and filtered and stored and so on. So when all that's done, then we're going to go ahead and get back a results stream of stream. So it's a two-dimensional stream. And we're going to use the Flatmap method to essentially get rid of the stream of streams and just have a stream of results. And we go ahead and take the stream of results, and we're going to go ahead and basically print the size of the URLs here, how many we just got done processing. And that's how we're going to get the results logged here. And then the very final thing we're going to do is we're going to call join to wait for all these images to be downloaded, processed, and stored. And then there's also another join out here at the outer level to wait for everything to happen. So I think you'll probably agree that this implementation is a bit more convoluted than the other one. The other one was a little bit sleeker, although the other one had this weirdness where we had the optional parameters, and that way we could ignore things earlier in the stream that had been passed down to us that didn't really have any sensible values. So that was just kind of the quirks of that implementation, but it's a little bit cleaner. This approach pulls out all the stops, shows all kinds of interesting things. If you take a look at the example, you see that we don't have any calls to collect here, which is really interesting in its own right in terms of how it works in a streams-like model. But if you run the tests, you'll see the performance results. Let's just go ahead and do that for kicks, just to reinforce the point that I'd made the other day, that there is a reason to do all these convoluted things with completable futures, and the reason for doing this is really performance. So you can see here, everything's up and running, going pretty fast. All my 6 cores are cranking away. And you can see that for the large files, then that completable futures 2 variant we just looked at, the convoluted one, that performs the best, followed by RxJava 2, which we'll talk about tomorrow, followed by completable futures 1, followed by parallel streams, and so on. So you can see that that complexity was worth it. And then down here, for the smaller files, we can see that the RxJava 1 implementation performs very well, followed closely thereafter by completable futures 1 and completable futures 2. So both completable future implementations run very well. And so in some sense, the pain may be worth the gain in terms of improving performance. So let me see if there's any questions at this point. So I have one more thing that I want to do right now, and that is take a look at yet another interesting variant of all this stuff. So I was having way too much fun yesterday and today, essentially playing around with different ways of dealing with asynchronous processing. And so I decided to showcase a couple of things. I wanted to showcase the combination of sequential streams and completable futures, and also use this to demonstrate the lazy processing of streams. So let me go ahead and see if I can compile and run this test. Hopefully it's still working. I've been fiddling around with it all morning. Okay, there we go. So it's still working. So here's what I want you to see. There's a bunch of sort of debugging statements and stuff in here that are just to show you where things are going. But let me go ahead and take a look at this thing. Whoops. Looks like it ran too far. All right, hold on. Tell you what, let's do. Let's go back into the code. And let's comment out some of the statements that are making it too verbose. Things are scrolling off the screen. Let's go ahead and get rid of this print statement. I think if we do that, that'll kind of clean things up a bit. Okay, so now you can see what's going on here. We're going to, a couple of key things here. We'll come back and look at this in a second. There's point 1, point 2, and point 3. And I want you to notice that point 1 occurs before any of the streams processing takes place. Point 2 occurs before any of the streams processing takes place. Then a bunch of streams processing takes place, followed by join. So just kind of keep that in the back of your mind as we talk about this program. And what I'm going to be doing here is showing you the laziness of streams. So streams only starts to run when some terminal operation is actually encountered. So let's go over here and look at this program. And this program, I wouldn't normally write code quite this linear. I was trying to show each step one at a time, and I was trying to show the laziness of streams. My natural inclination would be to group things together in a more intuitive way by having helper methods, which is a good idea. But here I really wanted to showcase kind of where things were happening. So it made sense to write it in one long linear stream or one long linear sequence of code. That is not my normal style. So please don't ding me for not using better modularization. All right, so we're going to process 10 big fractions. The main program starts our test and runs it. The first part of the run method is going to go ahead and make 10 random big fractions that are unreduced. We'll talk about what that means in a second. So a big fraction is just an arbitrary precision fraction. It has a big integer for the numerator. It has a big integer for the denominator. And you can have arbitrary precision fraction arithmetic. Not entirely sure why you need this, but it's a cool way to demonstrate some interesting aspects of completable futures and streams. So let's just stick with it for the time being. So we're going to generate 10 of these things. We're going to stick them into a list of big fractions. So that's just our input. What we're going to do now is we're going to go ahead and convert that big fractions list into a big fraction stream. And then we're going to go ahead and call the reduce big fraction async method reference on each element in that stream. So let's just pop down here and go look at big fraction async. I did it like this mostly so I could kind of make the code real simple to explain, and also gives me a good place to put a print statement for debugging purposes. So down here, we're going to take a big fraction, and then in the background, using the supply async factor method for completable futures, we're going to go ahead and reduce the big fraction, which will run in a thread in the common fork join pool, print out what the reduced fraction looks like, and then return that. So that all takes place in the background. Okay. Oh, and by the way, here's the make big fraction factor method. So we take a random number generator. We take a Boolean flag to indicate if we want to reduce it or not. We make ourselves an absolutely gigantic big integer as the numerator. We then create a denominator that's up to 10 times smaller than the numerator. So we've got really giant fractions. And then we make ourselves a big fraction with this giant numerator and this large denominator. And then we indicate if it should be reduced or not. We start out with it being unreduced, so we can reduce it later, because reduction takes a while. Okay, so popping back up here, what we now have is we have a stream of completable futures to big fractions, and we call that big fraction stream. What an imaginative name. And then down here, that's where I print out point 1 after first map. And I did that to indicate that nothing has actually happened yet. So no processing has yet occurred. And that's because streams are fundamentally lazy. They only run when they actually have to. And no terminal operation has been met yet, so they haven't started to run. The next thing we're going to do is we're going to convert the big stream into an array of completable futures to big fractions. Then we're going to use the arbitrary arity method to convert that into a completable future to a stream of big fractions. And all those things, when they run in the background, they'll all do their thing. And when they're all finished doing the reductions, which is what's designated by this map call up here, asynchronously, then we're going to get back a triggered completable future. So we'll get back a completable future. It'll be triggered when everything is done running in the background. When that happens, we take the futures, which is this array of completable futures, which are the ones that we were waiting for. We convert that into a stream, and then we map everything into a big fraction. So what we're going to end up here with is a completable future to a stream of big fractions. So that's what we're going to end up with after we do this operation. So completable future to stream of big fractions. Still nothing is actually run, and that's because when we print 0.2, if you go back and look at the run call here, you can see that nothing is actually going on at this point. No processing is taking place because streams are fundamentally lazy. So now we finally go ahead and do something useful. So at this point, when the stream has finished with, or at this point, we go ahead and we'll call collect on the stream. That triggers everything to start running. So when we call collect on the stream, we get a collector. It's going to collect, and it's going to go ahead and return essentially a list of big fractions. And now we're going to do something really cool with this list of big fractions. We're going to use the ThenCompose method, and we're going to go ahead and call this sort list method reference. And you can see what sort list does. This is super cool. Sort list takes a list of big fractions, and then we go ahead and we asynchronously quicksort the list, and then we concurrently merge sort the same list. So we're quicksorting and merge sorting the same list because I've got cores galore on my computer. And then we use the apply to either method, which is going to take either the quicksort or the merge sort and return that as a result. So whichever one finishes first, we're going to take the result from whichever of these sorts finish first. So if you remember your algorithms class when you were an undergrad, they probably spent a lot of time analyzing the asymptotic time complexity of quicksort and merge sort and bubble sort and insertion sort and merge sort and so on and heap sort. And you probably thought to yourself, who the heck cares? This is all so esoteric and so algorithmic. Well, it turns out now you don't have to sit there and do this analysis anymore. You just run multiple sorts in parallel using an ensemble method, and then let apply to either, pick whichever one happens first, and return that result. So we end up with a completable future to a list of big fractions. And as you can see back up here, when that is returned, when that computation is finished, we now have a sorted list, and then we call then accept on the sorted list, and we pass in the print list method reference, and you can see what that does is it just walks through the sorted list and prints out each fraction as a mixed string. And that's exactly what you can see happening here. You can see these things are sorted in the order, in ascending order. And then the last thing we do here is we go ahead and we just join on all of this stuff. So if you take a look up here, after print list gets returned, we join on that particular completable future. That's what makes everything kind of wait until everything's done running in the background. And then the final thing we do is we print 0.3 after join. So that way you can see sort of at a glance when things are running. And you can see that nothing really starts to run until after those other calls that we made that weren't doing anything because streams are evaluated lazily. So this particular example I think is kind of fun because it illustrates the laziness of streams. It illustrates how you can combine streams with completable futures. Once again, it's got some interesting stuff in here. It's got a big fraction class. If you're ever in the need of a big fraction class, here's a big fraction class. It's got this stream utils helper class that lets you work on essentially lists of completable futures so you can get a single point of weighting back, and just shows off a whole bunch of cool stuff. So that's essentially what I had planned to cover today. Let me just give you a quick recap or pre-cap, I guess, since we haven't done it yet, of what we're going to cover tomorrow. So in tomorrow's lesson, we're going to go back over here to ImageStream gang, and we're going to look at the RX Java versions of all this stuff. So here's ImageStream gang. You go into the folder repository, go down here into streams, and tomorrow we're going to take a look at the ImageStream RX Java 1 and ImageStream RX Java 2 examples. And they are also super cool. So they also run very efficiently. So by the time we're done with tomorrow's lesson, you will have received the Rosetta Stone of apples-to-apples comparisons between sequential and parallel streams, which was yesterday, different variants of completable futures, which is today, and then some different variants of RxJava, which is tomorrow. So that'll give you a very nice holistic perspective on how all these different mechanisms work. And you can really kind of compare and contrast them in terms of performance, in terms of complexity of programming, and you can decide what's best for you based on what your interests and what your needs are. Okay, well, I think that's where we're going to stop today. So if there's no questions, I will look forward to seeing everybody again, hopefully tomorrow.